We're going to go over a very fun and interesting problem today. It's number 20, valid parentheses. This is a LeetCode easy. Let's go over the description. Given a string S containing just the characters that you see here, determine if the input string is valid. An input string is valid if the following. Number 1, open brackets must be closed by the same type of brackets. Number 2, open brackets must be closed in the correct order. Again, this is where I recommend you pause the video and you ask the questions that you think you would ask the interviewer. Something like, are these the only things that we can expect in the string, or is there an off chance that we might see spaces and have to handle alphanumeric characters and things like that? Another question I would ask is S, is there a chance that S might be empty? You know, in LeetCode, when we're doing these problems, we get used to not asking these questions because we see them in the edge cases. Like when we submit, it fails, and we see, oh, it's because I didn't handle empty, I didn't handle this. But in a real life scenario interview, be sure to ask questions that you need clarifications for. Very, very important. All right, examples. Example number 1, we have, obviously this is valid because we have two matching parens, an open and closed paren. We have the same thing here. There's no matching paren or bracket here, so it's false. Same thing here. And then last but not least, you could see that we have matching opening and closing characters, but we also have to handle nested ones. Okay, so next step, I'm going to show you guys how to solve this problem in the whiteboard. All right, so I'm new to this whiteboard that I just bought, so just bear with me. So let's get started. All right, so here's the S. So consider this being S. This is a string that we have, and we're going to iterate over this string. So we're going to be at the very first index. Now, how are we going to handle deeply nested things like this one? And how are we going to validate this string? Well, we're going to go into a Rolodex of data structures, and we're going to pull out, yes, that's the one that we're thinking about, the array, or stack in our case. So we're going to have a stack. Oh, snap. What happened here? Let me erase that again. Like I said, I'm new to this thing. So I'm learning. So here, let's erase this thing. Let's change the color because that doesn't look that good. Let's go to orange. Okay. So let's do a stack. So here's our stack. Wow, that's pretty. So how is our algorithm going to work? We're going to leverage this characteristic in a stack, which is LIFO. LIFO, last in, first out. And we're going to do the following. We're in our first index, we're going to go, does this particular open paren have a matching closed paren in the stack? Well, it doesn't, right? So what do? We push it. We go to the next one and we ask the same question. Does this one have a matching closing one in the stack? It does not, so we push it to the stack. And we go to the next one and we do the same because there's no matching. And then here's where things get interesting. When we're at this index, we ask ourselves the same question. Does the following have a matching closed paren or closed character in the stack? Yes, it does. It's right here. So what do? We pop it from the stack. So we pop it from the stack. And again, all these things are constant time lookup, right, for it, because we're popping from the stack, popping from the end of the stack. It's constant time. And then also peeking, which is what we're doing to see if we have a matching. That's also constant time because in a stack, we're looking at the top of the stack and we have the index for that. So we're able to also do that in constant time. Let's keep going though. So when we're here, we do the same thing. Does it have a match? Yes. So let's pop. Let's pop it. And there you go. We pop it. We go to the next one. And we're here. Does it have a match? Yes. And then we pop. Pop, 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 pop. And then we go to the very end. We're now out of the for loop. And if the stack is empty, we return true. And that's the gist of our algorithm, guys. It's super simple. It's something that you have to seen in the past to kind of come up with this in an interview setting. So this is why we're doing this problem, to build up those fundamentals. Now let's implement this in code now. So some of the starter boilerplate stuff that I would have here is I would declare the stack and also a map, right? As you can see here, we have this map and we have the stack, and you're gonna see this stuff right here, and it might look odd to you at first. The reason we're doing this is because if you remember going over this when we're in here, or whenever we're here, we have to look for its opposite closing character, right? And that's why we have this right here. And you'll see this will make a lot more sense when we're going over that actual logic. So let's just go over it, right? Let's go for let I equals 0 while I is less than s dot length. So we're going to iterate over every character in s, and we're going to grab the current character in the index that we're at now. So cur equals I. And then here's where we're going to check if there's a matching one in the stack, right? And we're going to call this one peak. And this is basically what's at the end of the stack, the character that's the end of the stack, or the most recent one we push to the stack. And we're going to do a few things here. We're going to go, does map.has, and this returns a Boolean, does it have the current one? Why do we want to do map.has? Because let's use this example here. The reason we want to do that is because we really don't care to check for ones that are an opening character. And let's say we have a stack here, so the stack is empty. So here we're at an opening, right? Here's the opening. The openings, I didn't add them into the map because we don't really care for them, because when we're at an opening, we don't really care to find its match because it doesn't exist yet, right? Because we're at the opening. So we just skip it. So we go if map.has, in this case it wouldn't, right? So we need to take care of the else. So if it doesn't have it, then we push it to the stack. So we push cur. So now our stack is going to have this. Now, when we go to the second index in our S, this is where we're going to leverage this map.set here. So our cur now has this closing paren, and our peak, if you look at our peak, is the most recent thing we push to the stack, which is this opening paren, right? So we're going to say if map.has, and does map have this closing paren? Yes, it does. It's right here. And we need to do also the following. We need to make sure that it matches what's in the stack or at the top of the stack. So we do and map.get cur. So map.get cur basically gets the value of the matching key. So our key is this. Here's our key. And get basically returns this value. So is it equal to our peak, right? Which is this. And if you can see here, here's our opening. Here's our closing paren. Map.get, so it returns its opening. Does the opening exist in the stack? Yes. So we have a match, right? We have a match of a closing and opening paren. And because we have a match, we pop from the stack. Pop from the stack. This thing gets popped. And now we have an empty stack, and we go over it. We're not done with the for loop. And like we mentioned before, we're going to return true if stack.length is equal to 0. All right, so let's see if this works. Let's run it. True. Let's submit. There you go. Faster than 68.16% of JavaScript online submissions. All right, so without further ado, let's go over some important things. What's one of those? What is the space? Whoa, I'm getting ahead of myself. What is the time complexity of this? Time complexity equals, well, let's think about this for a second. We're going over every character in S, right? So we're going over every character in S here. And we're doing work at every character in S. What are we doing? What's the work that we're doing at every character in S? We're checking if it's in the map, and we're getting it and comparing it. Well, and we're also peeking. All these things, the peek, the map.has, the map.get, and the comparison, these are all done in constant time, right? At every iteration, these things that we're checking here are all done at constant time. Big O1. So what does that mean for us? That means that worst case scenario is, well, yeah, worst case scenario is we're going to go over every character in S. And doing so gives us big O(n), right? Because we don't have to do any further nested for loops or anything like that. So big O(n). Cool. Last but not least, space. Space, right? So what is our space? So our space in this case scenario is our stack. So what is the worst case scenario that could happen? How big could our stack grow? So let's say we have S, our S that we get from this function is a bunch of just opening, right? It's a bunch of opens like this. They're all openings, right? So we can never really pop them from the stack because they're all opens. So our space, our stack is going to grow to the same amount of S, and that is in the worst case. So that means space is equal to big O(n). And there you go, guys. There you have it. I hope you enjoyed it. We're learning together at the same time with this. So if you have any questions, shoot them in the comments. Don't forget to like and subscribe. I'm going to be coming out with a lot more. And yeah, like I said, any questions you have, leave them in the comments. I'm super quick on the trigger to respond. And I hope you guys have a good day. See you guys soon.